Okay, here we go. Welcome back. Whoops, I think we got some bad. There we go. That should be better. Um, Here's the good news, you guys. I think we're going to be able to finish lesson two. We're going to finish all of chapter 19, so there will not be a lesson three to watch. The downside is this is kind of complicated, so stick with me. All right, we're going to talk about a phenomenon that happens with thin films. You get interference patterns. Um, and you see this all the time, like the first day it rains in the fall, and you go out in the parking lot, and there's been a little oil on the parking lot. When it rains, you get this thin film of oil that floats on the water then, and you get to see a little rainbow in it. Another time you might see it is if you see a soap bubble in the air, you'll see a little rainbow in the soap bubble. And you go, what the heck is that? Another common application where you use this is in coatings on glasses for anti-reflective coatings. And we're going to talk about all that. You're going to learn how it works. Okay, we got to go back and remember a couple of things. First is constructive and destructive interference. You recall constructive interference, if you have two waves that are superimposed and they're in phase, you will get a much bigger peak and trough. This makes a light bright. Destructive interference happens when you get this superposition and they are a half a wavelength out of phase. You add the amplitudes and you get zero wave, which means dark. So bright, dark. The other thing is reflection and refraction. Reflection, of course, is when a wave comes in and it bounces off, some of the energy bounces off the boundary. And refraction is that same wave can hit a boundary and some of the energy is transmitted and it gets refracted. The other thing to remember on the reflection is if you're going from fast to slow, you're going to get inverted wave, if you recall. And when you're going from slow to fast, the wave will be upright that is reflected. Okay, got all that. Great. Now let's look at a situation. Let's assume that if anybody's been to the Exploratorium, they have this demo where they pull up a film of soap. It's a big, big sheet, and they've got like a dowel up here, and the soap film is like this coming out of a big puddle down here. And you see the rainbow reflected in that sheet. Let's look at that sheet of film, not from the front, but let's look at it from the side. Okay, so I've now cut it, and we're looking at the side, and what happens is it's thicker down here at the bottom because gravity will pull some of this liquid down. It's mostly water, right? Okay, so now let's look at what happens when a light ray comes in and hits it. All right, this comes in, and we'll kind of call this ray 1. By the way, the book has a really good description of this and better drawings than I'm going to be able to do, probably on page 527, so you may want to review that. Okay, some of the energy is going to get reflected, and it's going to come off here, and it's going to look like that. And this is the ray 1, right? And of course, you draw the normal here, and you'd see that the angle in is equal to the angle out, law of reflection. Some of the energy of this ray is going to get transmitted, and it's going to get refracted until it goes and travels and hits the back of this film. Then that too will get reflected up, and it will come out, and it will go parallel to ray 1, and we'll call this ray 2. Okay, these two rays aren't going to be right on top of each other, but you can see there's another ray just down here that will be right in sync with ray 2. So this is going to be the interference. Okay, let's think about what's happened here. This film thickness, whoops, this is a lambda, and this is a lambda. This film has some thickness of T, right? Ray 2 has to travel thickness to get to the back wall, and then another thickness to get to the front wall, right? So it's going boom, boom. It travels an additional distance of 2 times whatever the thickness is. Now, if that equals 1/2 of a wavelength, what's going to happen? Well, you would think that ray 1 travels this, whatever distance. Ray 2 travels the same distance plus 2 times the thickness. Or, if that's lambda over 2, lambda over 2. That would mean then that this ray 2 has traveled a half a wavelength further than ray 1. And so you'd think you would get destructive interference. So if this is ray 1 traveling along, ray 2 has to travel a half a wavelength further, so it's going to look like this. And you would think that you would get destructive interference and it would be dark. But in fact, what's happened is ray 1 has been inverted. So while ray 2 has traveled this extra half wavelength of difference, if you take ray 1 here, this is 1 and this is 2, and you invert it down here, you'll see that it is going to be like this, right on top of ray 2, ray 1, right on top of ray 1. And so what you're going to get is uber bright light. Okay, so this will give you constructive interference. And that is only, though, when the thickness is equal to lambda over 4, or lambda is equal to 4 times the thickness. Now, that color is associated with whatever wavelength it is. Now, here's the downside. If you recall, you've got lambda in a vacuum out here. Wavelength is going to change in the film, right? So the wavelength here has to be the film wavelength, not just the wavelength in the air, because it's changed in this medium. If you recall, N is C over V, and if you substitute in here lambda vacuum frequency, and here lambda film frequency, these cancel out, you will find that the lambda in the film is equal to lambda vacuum over N. So I have to substitute that in up there. Okay, so if the thickness of the film is equal to lambda vacuum over 4 times the N of the film, you will get a bright spot for that guy. Okay, so you see this all the time in different points. And then you can also imagine, let's say you come down a little further, and you've got now, this is thickness 1. Down here you've got thickness 2. It's a different thickness than thickness 1. So you would get a color that would be different than up here in terms of it being a bright spot. But you can also see that this will repeat every half a wavelength, right? And so you get this rainbow effect all throughout the film. By the way, I forgot to bring this up. I told you I would do this better next time, but I didn't. Here is the summary of the initial case where you'd think this ray 2 has traveled a half wavelength further. But in fact, since wave 1 is inverted, they're in sync. And so that's the 2 drawings there that you missed. Okay, I want to do a quick sample problem for you. And that's going to be number 6 from the book. Just so you have this for a kind of reference. Okay, this is a glass lens, and it has a this is number 6 book. It's a glass lens that has a non-reflective coating. And so what that does is it prevents, the coating is magnesium fluoride and it's placed on glass. How thick should the non-reflective layer be to keep yellow-green light with a wavelength of 555 nanometers from being reflected? Okay, the example that I showed you, we had constructive interference, right? Here we want destructive interference. So in other words, we want these to cancel each other out. So if we've got this situation, here is air, here is my magnesium fluoride coating, and it's some thickness, we don't know what, that's what they want us to find. They do tell us though that it has an N of 1.38, N for air is equal to 1.0, and it's sitting on glass. These are your glasses. And the reflective coating here, the index of refraction down there is 1.52. Okay, the question is, how thick does this have to be in order to make this a dark spot? Okay, so ray 1 is going to come down. It's going to hit and it's going to be reflected. So this is ray 1. Ray 2 is refracted, reflects off of here, and comes back up here. We want ray 1 and ray 2 to be a half a wavelength out of phase to get destructive interference. Okay, here's the other fun thing about this problem. In this case, we're going from air to magnesium fluoride, fast to slow. So ray 1 is inverted. Ray 2 is going from magnesium fluoride, and it's bouncing off then of glass. That's also going from fast to slow. So it too is going to be inverted. So now we need twice the distance to equal lambda over 2 in order to get destructive interference, because they're both inverted, right? So this thing travels twice as far, it will be a half a wavelength out of phase with that. Okay, the only thing is we have to use lambda in the film. And I can either calculate lambda in the film equal to lambda vacuum over n film, or I could just substitute it in here. Okay, so what we're going to do this calculation then is D will equal, we're going to solve for that, lambda film over 4, which is going to equal lambda vacuum over 4 times n film. And that equals, we were told we don't want to see 550 nanometers. 4 times 1.38 is the n for the film. You do this calculation and you get 101.5 nanometers. So I put 101 nanometer thick film onto my glasses, and this wavelength will not come out. It won't be reflected. And you also see that sometimes you see the ultraviolet, the coatings on glasses. Some glasses don't allow ultraviolet through, so it all gets reflected off, and you see people's glasses when they tilt them up and down look kind of bluish, same sort of thing. Okay, I'm sure there's going to be lots of questions on this, so give this a look and then let's hang out. Okay, that's the end of chapter 19. Good news.